Welcome to feedback amplifiers theory and analysis. In this video we'll see a few more examples of negative feedback amplifiers, and we'll also see at the end types of feedback possible for amplifiers. We were looking at what is the how does the negative feedback will reduce the noise effect, that is the reduction in the interference effect. So we obtain that output voltage with the feedback will have the signal component amplified by A1, A2 due to the feedback factor because of this feedback beta. And of course this was the expression for the signal component, and this is the expression for the noise component. If we take the ratio of signal to noise ratio, so it happens to be A2 times Vin by Vn. So where Vn by Vn happens to be the signal to noise ratio at the output without feedback network. So this is again SNRO, which is due to an amplifier only A1. So at this point we're going to have Vs and Vn, both are amplified by A1 times. So the ratio of signal to noise happens to be Vs by Vn even at the output. So signal to noise ratio at the output without feedback is this. This is signal to noise ratio at the output with feedback. This F is actually suffix for with feedback. So signal to noise ratio with feedback is A2 times signal to noise ratio without feedback. So A2 is the gain of this A2 will always decide what will be the improvement in the signal to noise ratio at the output of this the feedback. So that's why most of the amplifiers we always have a very high input RF amplifiers which will be of very low noise. So here we assume that okay, this is not introducing any noise here. So this is a noiseless amplifier, even though this A1 has got some noise. Since you have at the input stage a very high gain lossless noiseless amplifier, so we're going to have a very improved signal to noise ratio at this point. So we will consider an example. Okay, how does this interference will reduce because of this negative feedback. So here we are considering an output stage A1 with voltage gain as 1 volt per volt, because it is a power output stage. That's why the gain is hardly 1. The input amplitude is 1, and here the hum, that is the noise, is also considered to be 1 volt. So assuming these powers, and it is passing through a power amplifier. So and then prior to this power amplifier they are having a small signal amplifier with a gain of 100. So and there is a feedback given with beta equal to 1, and if the values of signal and the noise are unchanged, so they are looking at what is the improvement in signal to noise ratio or signal to interference ratio. So that's what we have here. So this is the block diagram representation of that statement. You have A1, which is a power amplifier with a gain of 1. You have a A2, a small signal amplifier with a gain of 100. There is a feedback factor beta is equal to 1, and of course the signal as well as the noise amplitude both are 1 volt each. So this is taken as 1 because it is a power stage. That's why the gain is less. This is again the representation of signal to noise ratio of only the power amplifier without feedback. So this happens to be again the output signal to noise ratio without feedback is A1 times Vs divided by A1 times Vn. This is signal to noise, so it happens to be 1 here. So after providing the feedback, you have a feedback amplifier A2 prior to A1 here. So now we can find out. This is a setup that is used to improve the signal to noise ratio with negative feedback, and you can see there is an amplifier with gain A2 preceded by the actual amplifier, power amplifier with a gain of A1. We will the expression for the signal and noise. You can see this is the input voltage, which is Vs here. So this is the signal is actually 1 volt now. Of course this is the magnitude we want to have. This is 1 volt, and if you can see the noise because of this feedback of beta is equal to 1, whatever input you have, almost same thing is coming down here. So it's almost 0.99, whereas if you see the noise component is hardly 9.9 millivolt, which is almost equal to 10 millivolt. So you can see the noise noise magnitude has reduced drastically compared to the signal. So then signal to noise ratio with feedback is given by this A2 into SNR O without feedback. Now what is this SNR O is actually 1 here. So this is actually 1 what we found out in the previous case. This is SNR O. What is this A2 is actually 100. So A2 is the gain of this second amplifier, which is preceded by A1. So if you can take the ratio of this by this, that's also 100. Or because this happens to be it is signal to noise ratio of signal by the noise of this particular setup is 100, which is also equal to A2 times signal to noise ratio of the output without feedback. So what we're going to have is the signal to noise ratio without feedback was actually 1. It is now improved by 100 times, so that there's an improvement of 40 dB in terms of signal to noise ratio. One of the question was it was asked for to find out what is the improvement in the signal to noise ratio. You can see hence the improvement in signal to interference ratio. Signal to interference ratio is now 40 dB with the feedback. So earlier it was almost 0 dB. So because 20 log of 1 is actually 0 dB. Okay, let us see what is this, how does the reduction in non-linearity will going to improve with feedback. Now assume that you have an amplifier. If you can see here, this is the x-axis is input voltage, the output voltage is put on y-axis. These are transfer characteristics. How does the gain of this amplifier varies? For very small amplitudes, you can see the gain of this amplifier is almost 1000. The gain of the same amplifier will become 100 as the input amplitude increases beyond this point, and any amplitude after a large value, the gain is almost 1. That is, it doesn't have any gain. The output is almost equal to input. Okay, this is not having any gain here. So what I want to say is for lesser amplitudes, the same amplifier has got more gain. As the amplitude of the input signal increases, the gain is keep on changing. So this is what is the non-linearity of an amplifier, because why this property is exhibited by an amplifier is because amplifier is going to have a transistor which is a non-linear element as an active element in that entire circuit. So this non-linearity over the input voltage has to be reduced. So that can be reduced using the negative feedback. I can see now the same amplifier which was having a gain of 1000, 100, which is keep on changing for different amplitudes, has been provided with a negative feedback beta. In this particular case, we are assuming beta to be 1%, that is 0.01. If you can see here, the overall gain of the amplifier which was changing from 1000 to 100, you can see the amount of change is almost 10 times. So this 10 times reduction over a range of input voltage from very small amplitude to large amplitude, you can see the change is from 1000 to 100. Upon doing the feedback by substituting A as 1000 and beta as 0.01, when the gain, the open loop gain is 1000, the closed loop gain with the feedback is 90.9. When the open loop gain is 100 for this amplifier, so its gain is 50. If you can see, this change from 90 to 50 is less than 2 times. So it is not reduced less than, okay, it is reduced by less than 2 times, whereas without feedback there was a reduction of almost 10 times. So if you can see this line, the below line, it almost looks like a straight line, meaning there is no much non-linearity over the range of input voltage. Whereas you can see the top line, the input voltage, as the input voltage is changing, you can see this is having a sharp gain, and you can see the gain is reduced. Whereas here in the second line, the gain is almost fairly constant over a large range of input amplitude. So that's what you mean by reduction in the non-linear distortion of the amplifier. So over a large range of input voltage, the amplifier will almost behave with the same gain, even though there is a small change, but this is far less compared to the amplifier non-linearity without feedback. So with feedback it improves. You can see it almost looks like a straight line. We will see the amplifier feedback topologies. So there are different topologies, the way how you do the feedback of signal from output to input. This is what you have an amplifier. There's a feedback, so there's a negative feedback here. We're going to have a source and load. We'll see first and foremost thing, this is the feedback topology. We call it as series shunt feedback. If you can carefully notice this is a basic amplifier, this is a feedback network, and you can see there is a source. You have taken the output voltage here. This RS and RL happens to be the source resistance and the load resistance. Okay, if you can carefully notice this is an type of feedback. It is called as a series shunt feedback. You can see this phenomenon is voltage mixing and voltage sampling. So we have an amplifier. Here the voltage is being mixed with the existing input voltage, and what you are sampling is also an voltage, because what you are adding is voltage, what you are sampling is also voltage, meaning the input is voltage, the output is also voltage. Naturally this has to be applied for basic voltage amplifiers. All voltage amplifiers have to have this type of feedback topology, where you are sampling the voltage, because we know that voltages can be sampled by connecting it in shunt. Voltages can be added only in series. You can see we are adding the voltage in series, whereas we are sampling the voltage in parallel. So it is voltage mixing and voltage sampling. Why it is called as series shunt feedback is, if you can see, the input is added in series, whereas the output is taken out in shunt. So this is how you are sampling. And how do we say that this is negative feedback is, if you can see the input to this amplifier is measured here, that is this is V in. So if you can actually write a KVL for this, the applied PS, the signal voltage, source voltage, is actually V in plus VF, that is feedback voltage, the feedback voltage. If you can actually note down what is this VI, that is, this is VI is actually VS minus VF, meaning to say, if there was no feedback here from the output to input, the VI would have been equal to VS. Because of this feedback VF, in this polarity, that is minus plus, we're going to have the input voltage is less than the previous case. So that's why the V in is VS minus VF. That's why this is called as negative feedback. Actually, for positive feedback, this will be plus, this will be minus. So we're going to have again a series connection here, that is they are coming in series, but this will be plus, this will be minus. That is for positive feedback. Since we are looking for negative feedback series shunt amplifier, it is serially added, it is sampled in shunt, and since the polarity is minus plus here, it's a negative feedback series shunt amplifier. And of course the basic amplifier has to be an voltage amplifier. We will see an example of this series shunt amplifier. So this is a very basic amplifier. Here you can see this is a non-inverting amplifier. If you can carefully notice here, so we have an input voltage Vi here, this is Vi plus minus, this is output voltage, a portion of it is being sampled. The sampled voltage is V0 into R1 by R1 plus R2, this is what is VF. If you can again write the KVL here, the input voltage is Vs minus Vf. So that's why you can see, since you are sampling the voltage and adding the voltage in such a polarity that the input voltage is less by the feedback voltage. This is an example of series shunt feedback. Again, a similar type of example for series shunt using the transistor MOSFETs. You can see this, you have a CS amplifier with source degeneration, and you can have you have one more CS amplifier. You can see this is the output voltage is being sampled and then fed back here. Again, if you write the KVL for this, the input voltage with this polarity is actually Vs minus Vf, that is source voltage minus the feedback voltage. So that's why this is voltage shunt and voltage added, but voltage is added in this polarity, that's why this is also negative feedback.